Today we'll begin our lecture on the ocean currents. The currents, of course, derive their energy from the sun in the form of radiation which falls on the Earth. Now at the equator and in the vicinity of the equator, the sun is almost overhead, so the energy falls directly on the surface of the Earth. But at the poles, of course, the energy falls at an angle, so the amount of energy, radiant energy, per square mile, say, is very much less. This creates an immense heat engine, which is the first topic we will talk about. But in addition to this, the oceans give up energy to the atmosphere and drive our atmosphere. Now, you are well aware, of course, that wind blowing on the ocean or on any body of water causes the water to move. And such is the case for the oceans. The major wind systems of the world create the large ocean gyres and currents such as the Gulf Stream. Before we begin, we must realize that the Earth is rotating, and this creates a force which is of immense importance in oceanography and determines the actual characteristics of the ocean currents. And the force is called the Coriolis force. If we can imagine our Earth rotating like this, and let us imagine that there is a satellite circling the Earth. Now, if the Earth was still, we might suppose that the satellite would run over the pole, then pass over the eastern side of South America, and continue on its course around and around the Earth. And an observer, if the Earth was still, sitting here, would see the satellite pass the pole and then pass the western side of South America. But of course, we are essentially in space, and the observer on the Earth is moving. So when the satellite passes in its orbit, the Earth actually is rotating like this, so that when it arrives at the equator, it could, for example, be over the western side of South America. Now, to the observer in space, which is us, the satellite is still going in a circular orbit around the Earth in the same plane. But to the observer on the Earth, who started off at this point, the satellite apparently is following a curved path. Now, this means that to an observer who is actually on the Earth, there is actually a force directed to the right in the case of the northern hemisphere. It's not an actual force, it's an apparent force. And if he is in the southern hemisphere, there is a force directed towards the left, and this is called the Coriolis force. It's important in things like artillery. When one calculates this force, one finds that this apparent force is a maximum at the poles and in fact is zero at the equator. And it's going to pervade all our discussions from now on. Now let us first of all turn to the heat engine, the motion of the oceans, which is caused by the difference in radiation at the poles and at the equator. And here we have a diagram which illustrates this type of circulation. This is a diagram with the equator on the left and the pole on the right, and the ocean absorbs heat near the equator, which causes the surface waters to be warm. At the poles, heat is extracted from the ocean, and therefore the water becomes colder, and as you know, colder water is more dense. The result of this is that the dense water sinks, flows along the abyssal parts of the ocean, and then gradually percolates to the surface through diffusive processes and upwelling processes. The form of these processes is really not very well known. It is really quite slow, and averaged over the ocean would amount to an upward velocity of not more than 1 centimetre per day. Then the return flow is at the surface from the equator to the poles. And this is called the thermohaline circulation of the ocean, and creates the circulation in the abyssal parts of the ocean. Let's first of all look at a diagram of the ocean and ask ourselves, how are these flows traced by oceanographers? Well, since the water is cold when it goes down and the surface is heated near the equator, one would expect there would be a temperature gradient, and in fact there is. And the oceanographer traces these flows by observing the temperature of the ocean. And here we have a typical section of the North Atlantic Ocean, which shows the temperatures in the deeper parts of the ocean. I've left the surface out, and we will deal with that in a later lecture. But this is the south, towards the South Pole, 60 degrees south. Here we have the equator, and here we have 60 degrees north. And the Atlantic Ocean has a very irregular bottom. It's almost over 6,000 meters deep in parts. And in the southern part of the ocean, we find that the temperatures are in fact below 0 degrees, which they can be because the ocean is salt. In fact, they can become as low as about minus 1.9 degrees centigrade before freezing occurs. Then we have a body of water which is between 0 and 2 degrees centigrade, then a body of water between 2 and 4 degrees centigrade. Now, by looking at charts such as this, the oceanographer really tracks these flows created by the thermohaline circulation and determines where they go. Now, obviously, there is a flow of very cold water, less than 0 degrees, in the southern part of the Atlantic Ocean, which is gradually moving north. There is another flow in the northern part of the Atlantic Ocean, which has descended and which is moving towards the south. Now, the flows are also tracked by temperature and salinity, and the flows across the ocean in the latitudinal direction, of course, are not constant in temperature and salinity, and by making temperature and salinity measurements throughout the ocean, it has been possible to chart the path of these abyssal currents. The type of basin that these flows are flowing into is illustrated on this slide here. This is the topography of the Atlantic Ocean. Here is America, and here's Africa and England, and down the center of the Atlantic Ocean there is this range of mountains called the North Atlantic Ridge. This, in fact, is created by continental drift and the fact that the continents are drifting apart. So, in effect, in the Atlantic Ocean, we have two sets of basins. We have an eastern set of basins, like this, and we have a western set of basins. And these are called the eastern basins, and the others are called the western basins. And there are, at places in this ridge system, gaps. There is a gap south of Iceland, at the foot of the Reykjanes Ridge, called the Gibbs Fracture Zone, and there is another gap at the equator called the Romanche Trench. And through these gaps and trenches, the abyssal water flows from one basin to the other. Now, using the charts of temperature and salinity, it has been possible to trace these flows in latitudinal extent. The very cold water that we saw in our diagram a little earlier originates in the Weddell Sea, in this area which I have indicated with a black dot. And it spreads north in the Atlantic. Now, because of the Coriolis force, this northerly flowing water is forced to the left. And so we have the strongest flow of this bottom water, as it is called, along the western side of the ocean. And it gradually moves into the North Atlantic, and by the time it gets to the area of Nova Scotia, it's gradually lost its identity. Some of this water, the Antarctic bottom water as it is called, moves north and goes through this gap in the mid-Atlantic ridge called the Romanche Trench, and it spreads out to cover the bottom of the eastern basins. Part of it, in fact, moves off around the bottom of the ridge and into the Pacific, and it covers the complete bottom of the Pacific as well. The next flow, of course, is the northern flow, which we observed, and this originates in two areas in the North Atlantic. One is in the Norwegian Sea, the area between Norway and Greenland. Now this actually is an ocean basin, and between England and Iceland, and between Iceland and Denmark, there are a series of ridges called the Wyville-Thomson ridges. And this water is cooled in the winter. The oceanographers frankly don't know exactly how this process happens, but they do know it is cooled and that it sinks and that the bottom of the Norwegian Sea is filled with this deep cold water. And then it spills over these ridges like an immense cataract. It's actually an undersea waterfall, if you like, and the speed of this can rise to 2 to 3 knots, that's 2 or 3 miles an hour, and it spills over these ridges into the Atlantic Ocean. The part that comes over in the Denmark Strait just spills over and sinks straight to the bottom, and the part which comes over between England and Iceland spills over the ridges, and again by the Coriolis force it is forced to keep up against the mid-Atlantic ridge, and eventually it finds its way through this gap in the mid-Atlantic ridge and joins the other flow from the Denmark Strait. And this forms the bottom water in the North Atlantic. The other area is in the Labrador Sea, where again sinking occurs in the winter time. This has actually only been observed once. As a matter of fact, it was last winter by a Canadian ship, the Hudson. But it is known that this body of cold water exists there. It's, because of its salinity, it's a little lighter than the water which comes over the ridges from the Norwegian Sea, so it sits on top of it. And then the three flows of water eventually mix themselves together and create a body of bottom water which flows down the Atlantic. Now again, because of the Coriolis force, it is compelled to flow on the western side of the ocean. It flows down the Atlantic all the way down into the South Atlantic, and it also goes round the tip of South Africa into the Pacific. And this flow of water has been traced as far away as off New Zealand. The northerly flow of water is in fact a little less dense than that which we saw earlier coming from the south, so it sits on top of it. Well, this circulation is called the thermohaline circulation. Now let's look at the wind-driven circulation. The wind blows on the water, and of course it creates waves which absorb a certain amount of energy. But a certain amount of the energy goes into creating the surface currents of the ocean. It does this by a rather complicated mechanism, which we will sort of work through. Now, the first thing that happens, when the wind blows on the ocean, it creates what we call an Ekman layer due to a flow called the Ekman flow. Let us imagine this as a little section of the ocean, a little square of the ocean, with the wind blowing in the direction indicated by the arrow. Now, to begin with, the water is going to move in the direction of the wind. But as it moves, the Coriolis effect begins to be felt, and the water will in fact move to the right of the direction of the wind. Theoretically, some rather elementary calculations says that this water moves at 45 degrees, but we know this isn't quite correct. In fact, it's not really well known exactly what direction it, how many degrees off the wind it is, maybe 10 to 15 degrees. But so the surface waters in fact move to a little to the right of the wind. Now, because of turbulence in the ocean, one layer will interact and drive a lower layer. So if we could imagine the ocean is made up of a series of layers, first of all the wind driving the top layer, and then the next layer down driving a lower layer, and so on down through the ocean, we would find that the direction of the motion of the waters created by a wind in this direction would gradually turn to the right because of the Coriolis force, and naturally the energy will gradually get dispersed, and the velocity of the water will decrease. So here we have the wind, the surface water going this way, and so on down through the ocean, and we'll gradually get this move. And this is called an Ekman spiral. Now, in totality, if we looked at the mean flow of all this water, the mass flow, it would be directed to the right of the wind. Now, the Ekman layer, as it is called, is between 50 to 100 meters depth, and it occurs in the surface of the ocean. So what effect does this have on the waters below it? Now, the major ocean systems are driven by the permanent wind systems, and these impart to the water movement. And here we have a diagram of the Atlantic Ocean showing the permanent wind system over the Atlantic Ocean, over the north part of it. In the northern part of the ocean, we have predominantly westerly winds directed from Canada towards England, and these blow all the time. Of course, there are storms which move around, but generally the movement of the wind is in this direction. In the southern part of the Atlantic Ocean, we have the trade winds, and these blow from the east. So we have a countervailing set of winds, one around the equator in the southern part of the North Atlantic, and one in the northern part. Now, if we remember this Ekman layer we have described and the effect of the wind in the Ekman layer, the surface waters then are going to be forced to the right in the north, and they'll be forced to the right in the south. We're still in the northern hemisphere, and this will lead to a piling up of the surface waters in the upper 100 meters or so in this area called the Sargasso Sea. Now, it's not so much the piling up of the waters which are important, but the fact that they press down on the waters below them. Now, this pressing down means that the waters in the Sargasso Sea area are constrained to move towards the equator because of a rather difficult thing to explain related to the Coriolis effect. It turns out that if we have a column of water here, it has a certain amount of rotation. If it moves, it has to move to a place on the Earth where the rotation is similar to its rotation. So if it's squashed down, it loses rotation. It must move towards the equator where the Coriolis effect is smaller. So the net of this is we have a movement of the deeper waters, below 100 meters, towards the equator. Now, if this occurs in the ocean, there's got to be a return flow. These waters moving to the south have got to be replaced. Now, they can be replaced by currents on the east side of the ocean or on the west side of the ocean. Now, if we imagine a little column of water on the west side of the ocean, it's going to move north, and it's going to have to actually acquire rotation. Now, the only way it can actually do this is by friction against the continent. And if we can imagine a column spinning like this, clockwise, the only way it can lose rotation is by friction, and the only side of the ocean it can lose rotation, of course, is the western side of the ocean. If it spins up the eastern side of the ocean, by friction, it gains rotation. But in fact, it wants to lose it. And the net result is that on the western side of the ocean, we find these very intense currents. And here we have a diagram of the gyre in the Sargasso Sea created by that permanent wind system. And we have a very strong western boundary current, which, of course, you will know as the Gulf Stream. Now, these occur in all the oceans, and we have these large gyres formed, or eddies. And here we have a picture of the oceans and of the major ocean currents. In the northern areas, we have the Atlantic Ocean and the gyre we have just described, circulating like this, with the Gulf Stream flowing alongside the coast of North America. Because one of the things you realize with this explanation for these strong western boundary currents, even though part of this gyre goes through the Strait to Florida and emerges as part of the Gulf Stream, the fact that the Strait to Florida are there isn't necessary to have a Gulf Stream. In fact, if you close them off, you would still have a western boundary current. The Gulf Stream, of course, would be modified considerably, but it would still be there. In the northern Pacific, we have the Kuroshio current flowing past Japan. Again, a strong western boundary current with a gradual return flow on the eastern side of the ocean. In the southern hemisphere, we have, of course, the Coriolis force is opposite in sign. And this still induces, though, if we work through this argument that we did before, a very strong flow on the western side of the ocean. And so we have these counterclockwise gyres in the Southern Ocean. This is the Brazil current and a return flow past Africa. And in the Indian Ocean, in the southern side, we have a strong current on the western side of the ocean again. The Indian Ocean we'll deal with a little later because its wind system is different. It's influenced by the monsoons. The Southern Pacific, of course, is rather anomalous because there are no boundaries here. There is no land mass to direct the flow, and so there generally is not a western boundary current. In the Southern Ocean, where the wind systems actually circulate the Antarctic continent, we have the waters flowing all around the Earth. And of course, this is the only current which can circulate around the Earth. In the northern areas, there are other gyres, and here we have a very cold current, the East Greenland current and the Labrador current, and there are similar subsidiary current systems in around Japan and in the Southern Ocean. Now, we have now seen two types of current. We've seen our deep abyssal flow caused by the sinking of waters, the cooling and sinking of waters in polar regions, and we've seen the major gyres which are created by the wind. There's another intermediate body of water which is found over most of the oceans, and it is created by an interesting phenomena around the Antarctic. And here we have a picture of the Antarctic. This is South America, New Zealand, and Australia. And circulating the Antarctic, there is a strong wind system, permanent wind system. The effect of this wind, which I've indicated by the circular arrows, is to drive the water to the left. And so the water moves away from the continent. Now, because we are close to Antarctica, and there's a lot of ice melting in Antarctica, the surface waters tend to be rather fresh, a little less salty than the rest of the ocean. And they move north under the influence of the wind until they meet the warm, salty water of the major gyres of the ocean. And there they slip beneath the surface waters in the major part of the ocean and create an intermediate flow which is called the Antarctic Intermediate Water. And this flows below the Ekman layer but above the deep flows that we saw earlier. Now, let us put all this together and see if we can look at an imaginary ocean and the different flows which are really occurring in it. Here we have the Antarctic. This is a very schematic thing, but it will give you an idea of what's going on. Here we have Greenland and Iceland, and the Indian Ocean will be over the back. And we'll imagine this to be the Atlantic. Now, first of all, we had our deep flow of abyssal water from the Antarctic flowing down, flowing along the bottom of the Atlantic Ocean. Then we had the flows which formed in the Norwegian Sea, again through cooling of the water, which flow down, and since they're a little less dense than the flow from the Antarctic, they're a little warmer, these move along the top of the flow from the Antarctic. Next, this is two layers now. Our third layer of water, again, is this flow we have just described due to the convergence all around Antarctica. And these flows are sort of thermohaline flows. Then superimposed on these, we have the gyres which are created by the wind. Now, as you can realize, these flows of water are very difficult to put together. I wouldn't say that oceanographers really could completely describe what would happen to a particle of water and where it would go. But we do know that these are the general features of the ocean, and using techniques such as current meters, we are very busily trying to describe details of the flow. Now, in the next lecture, we are going to look at some of the changes which occur in these flows.